Amal.
Sir,
Akash.
we were
Yeah.
talking about the different properties and also.
Okay. Anyone? Vishnu? No. Akash? No one. Okay, fine. So in the last class, we have discussed about the annealing stages. If you remember, the three annealing stages we have discussed. One is recovery, then second one is recrystallization, then third one is grain growth. Okay, so also we have discussed about the mechanism, how it is happening and how in which way also it is happening. Then also what are the to make the recovery or to make the recrystallization or grain growth, what were the driving forces for that? That also we have discussed. Then also in the last we have discussed about the hydrostatic stress, almost like equal to the hydrostatic pressure. These are also we have discussed. And then finally we have discussed about the all the schematic diagram based on the this deformation zone geometry. Okay, so these are also we have discussed. So today almost we have covered everything, but only I will a little discuss about some relate to the research wide. So that's why I put one slide of the metallurgical structure. Because we when we are doing something, so we are telling that we have to put the raw material, and this is the technique. If you remember the beginning of the slide, I told you have some input, you have some technology in between, then you have some output. But also at the same time, we have to understand the basic mechanism. What also we have talked about the mechanics of the deformation process. Then finally, we have to go for a little bit of characterization, because technically how we can make there, or how we can explain there. So I put one example here. So this example is cold drawing an iron wire. Okay, so just only we cannot tell that we are just taking from a iron slab or iron plate to a iron wire, but how in a metallurgical aspect or how in technical aspect, how we can define, or how we can do the some process. So here you can see the whatever they have taken the sample of the iron wire for the cold drawing. So if you remember our normally the stress strain diagram, how it looks like. But here also when we are taking the iron wire, then also how it is going. For example, this is the true stress and this is the true strain. So you will find a graph like this, based on our these two stress strain diagram. Okay, so here how you have to explain actually, because this is important. You have to relate with some literature, what in the literature actually they have mentioned. Then the similar way also what we have studied from the book, that also you have to relate. Okay, so here it is mentioned that the stress strain curve determined after the wire had been drawn to a specific true strain are superimposed to show the overall strain hardening effect. Because from here also you have to correlate with the strain hardening effect what we have already studied. And also you can correlate with the in the upper part you can see the reduction in area by wire drawing percentage. Okay, because this is also related to the area. Okay, so for example, if you are talking about stress force per area, how much force you are giving, then in particular or with respect to some area. Okay, so you can see also, so whenever your strain you are comparing with the true stress, so I mentioned here it is quite remarkable that the rate of strain hardening does not diminish significantly even at strain more than 6. So that means you can compare maybe with some other research, probably they have not found this graph beyond 6, but here actually we are finding beyond 6 also we are getting. So you have to correlate like this. So that's why I put one graph here so that you can understand, right? Yeah. So one more part I have mentioned here, because sometimes when we are making some forging, or when we are changing the shape from one dimension or one shape to another dimension. So you can see here I put one more schematic diagram here, development of shear band in compression of a cylinder. Okay, for example, if you have a cylinder in the beginning initially, and the moment you are applying the force, and of course you have the velocity, you have the strain, you have the stress, then you have the force, everything, all the parameter you are looking. But at the same time, when you are changing this one from this shape to this shape, where it is mentioning increasing the reduction. That means the reduction is increasing from step 1 to step 2 and step 3. According to your requirement, you are just doing that one. Okay. But from here also you cannot tell that only I'm just pressing, so I'm getting this sample, or I'm getting this result. At least you have to again explain why this is happening. So that's why we have studied all the the mechanics, mechanism, everything we have studied. right? So here also I mentioned on a more macroscopic scale, the structure of severely cold work metal, because you have to correlate again to cold work or maybe hot work or maybe the warm work, is characterized by the development of a strong crystallography texture. Okay, maybe today also, of course, I will show one slide about the residual stress. Of course, we have already studied, but I will show you that in a schematic diagram how actually it is happening. Okay, so here also it is mentioned that closely allied with the development of a texture is the formation of a deformation band and shear bands. So that means here you are finding some deformation bands, and at the same time also you are finding some shear bands. So how to define the deformation band? The deformation bands are a region of distortion where a portion of grain has rotated towards another orientation. If you remember when we have talked about the recovery recrystallization, okay, I put some the T-shape structure. So that also one your the grain actually in one size, let's say you have, so it will rotate or it will orientate in some another shape or in another position. Okay, but with respect to the strength. So these are known as the deformation band. But the moment those regions, whatever the deformation bands we have, it extend across many grains. The moment you are just only considering one, but the moment we are considering across many grains, then these are known as the shear band. Okay, but after that, if you are going to the exhaustive shear along these bands in a common type of failure in work products. Okay, so basically when we are talking about the forging or maybe extrusion or maybe the rolling, so you are finding some deformation band because we are considering for one initially, but later you cannot find only one because you have a lot of grains. You know, when we have shown about the microstructure in the beginning, recovery, recrystallization, and grain growth. So that means initially you have the grains, then it will stretch somewhere because when you are applying the force or maybe in the deformation zone, then you are finding or you are creating some new grains there, and that grains again it is growing and it will become the in the growth stage. Then you cannot grow more, right? Is it clear? Yeah.
Yes, sir.
Okay. Then one more also in research aspects also I told, maybe probably you had whenever you have studied the the dynamics part in your other courses like mechanics of machine or maybe somewhere. So here also I mentioned considerable research in recent years has led to increased understanding of the mechanism of hot working, because all the the process whatever we have studied, cold working or warm working or hot working, so also many people they are interested how to find something new, because research is not limited to that what we are studying here. Okay, just I put some glimpse of some kind of research so that many people they will be interested. At the outset, it is important to distinguish between those processes which occur during deformation. So one is dynamic process, then and those which take place between interval of deformation and or after deformation is completed. So this is known as the static process. So that means in between when we are making the process or when we are giving them force, then you have some deformation zone, then this is known as the dynamic process. That means this is completely going now. The process is going. The process is not stopped. But the moment you have finished everything, so that means there after you are not making any deformation or any plastic deformation, we are known as the static process. So the two dynamic process involved in hot working are, one is dynamic recovery and second one is dynamic recrystallization. Okay, so these are almost we have covered everything in detail in the last class, but only we have added here dynamic recovery, and this is known as the dynamic recrystallization. And also I put one definition here how to define this dynamic recovery is the basic mechanism that leads to the annihilation. Annihilation means you have to make a full distortion. You are breaking that one because you are finding some dislocations there. So the basic mechanism that leads to the annihilation of pairs of dislocation during straining. So that means the moment you are making the straining and you have the dislocation there, so you are making some disorder there or you are making some distortion there. Okay, so these are known as the dynamic recovery, and it results in a flow curve that 1 order to magnitude lower than the cold working. Okay, and also you are getting some the stacking fault energy. So these are not, we are not covering here because almost you have studied in the beginning of your the material science or the sleep 2 in everything. We do not have enough time to again go back to that in material science what you have studied. And second thing, you have the dynamic recrystallization, and that dynamic recrystallization dislocation annihilation only occurs when the dislocation density reaches such high level that recrystallization occurs. So that means whenever your dislocant density which reach at the higher level, then this is known as the dynamic recrystallization. Whatever we have studied in the beginning, just we have added a little bit of in a metallurgical aspect. Okay, this is known as the dynamic recovery, and one is known as the dynamic recrystallization. And why we are considering this one? Because this affect to the deformation zone during the deformation, and that place only we have you are getting or you are finding. You are not considering the static one, because the static means it is already finished. You are not going to the other side, or you are not going to the fracture side. This is already stable there. You cannot have that option again to deform. Okay, fine. Yeah.
Yes, sir.
Okay. Yeah. So next one we have the workability. Okay, so workability also, how to define this workability. Maybe probably we have studied in machinability when we have done in the machining in the last semester. So here I mentioned the workability is concerned with the extent to which a material can be deformed in a specific metalworking process without the formation of crack. Okay, because that means you are not getting any crack. Maybe in the beginning somebody was asking about maybe some cracks or something, how we are getting, but how to probably how we can diminish that one. Okay, maybe some in a general way, maybe we have covered something, because in hot forging, if you remember, if there is some blowholes or maybe cracks inside, I told maybe 2 classes before. So if you can press it at that time, probably it will diminish there. Okay, so a lot of depending upon the material also you can make it. But this workability, it depends upon two factors. So one on the property of the materials, and is evaluated by some sort of small scale laboratory test. Okay, because what I told maybe in the beginning, normally in the laboratory scale, it is very difficult to find out a clear cut answer or clear cut research there, because we need a long process. In company only you can do, because this is a big scale industry or the large scale industry, you can do that. But some sort of small scale laboratory test, maybe when we can take some sample maybe from that area, or maybe we can go for some characterization, maybe that can, or that part is possible in laboratory scale. But normally we have to go for the larger scale. And the second function of the parameters of the deformation process, such as the die geometry, what we have studied in the last class, lubrication condition, and workpiece geometry. Okay, so these are also we have studied, because why we are using the lubrication, what should be the impact there, what we can get some the motivation or the advantage there, that are also we have discussed. Then workpiece geometry. Okay, that also we have covered in the last class. So these are the basic function or the basic parameter also when we are talking about the workability. Then also I mentioned one thing, two functions are brought together. These two functions, whatever we have talked about the the property of the material, we can do in the small scale or in the lab scale. And the second thing, the function which are related to the digeometry or the lubricant, that also we can combine in a diagram, or in a relate to a, or we can make in a diagram, or we can show in a diagram. So this diagram is known as the workability limit diagram. Okay, so I just mentioned here, I gave one more example here, how we can define, or how people they are making. This is a little bit of research oriented. So if you are interested, probably you can go, or you can do in your higher studies. So the example is of a bolt head is formed by a cold working, whatever I have shown here. So this is the initial, what will be our target. You have a rod here. Okay, so from the rod, and this diameter is d, small d, but you have to make a head actually. Okay, the upper head, the nail. If you remember the nail what we are using in the wall, so we can make from small d to the diameter of the capital D. Okay, so what should be the parameter actually we are thinking here? We are not thinking that just only we can hammer it, or we can make it forging, or maybe do some other process, so we can make this one. But what should be the parameters also you are taking? To form a head of diameter d from a rod of diameter small d requires the material to withstand the circumference surface strain of d by d. So that means it can withstand d by d, what we have already made some numerical based on this one. So if you will see, so let's say your material is, and this is the compressive strain here in the x-axis, and y-axis is the strain. Okay, so let's say your material is this one. So that means it is showing the strain of this line. Okay, material A, and the second one is material B, and these are the strain path we are getting. Okay, the upper part is the strain path A, small a, and the bottom part is the strain path B. Okay, so what I mentioned here, the strain path A, please remember this one, or read again carefully. The strain path small a does not meet this criteria, because what our main criteria is the strain path must reach this limiting value. So the limiting value is ln d by d. Okay, whatever I put here. So that means it must reach this limiting value. So in where if the strand path is not meeting this limiting value, so that means this path will not calculating, or it is not clear, or you cannot achieve by this. So what you will do, if you have to change the path B, then probably it is possible. So you have to do like this, because for example, you are doing one experiment, but let's say you are not getting the result. Then what you will do? You cannot stop the experiment. Okay, maybe in that case you have to stop the experiment, but if you will stop the experiment, only your waste of time and waste of sample. So what you will do, if you feel that this experiment is going wrong now, so there is no meaning now, so rather to stop this experiment, so just you can do some rough estimation there, or you can just play your with your mind that maybe if I will add this one, or if I will do this one, or if I will change this parameter, what will happen? Because of course this experiment is wrong now, this is not going well, you will not find any result from that. So you can play with that. So what I mentioned here, the strand path A, the strand path A small a does not meet this criteria, but by improving the lubrication to shift the strand path to curve B, a bolt head can be made without fracture. Okay, so that means if the strand path A is not good, because this is not reaching the line, but whereas if I will change something, so that means if I will change the lubrication or maybe some other thing, if I can change to strand path B, probably I can get that one. Right? Alternatively, a successful bolt head could be made with a strand path A. If also you can make in the strand path A, if the material were changed from A to B. So in another way also you can make it. So if it is possible, so instead of the material A, if you can change to material B also, maybe with the strand path A also it is possible. Right? Is it clear? In two ways we can make it. Is it fine? Or one time again I will explain.
Sir, could you explain once more?
Yeah. Okay. So what I'm telling, so for example, you have material A here, because what is our target? Our target is you have a sample of the diameter D. Okay, and you want to make the diameter of capital D here. Okay, you have a small rod, but you want to make it the diameter D. This is the main aim of. Okay, our aim is like this. So now question is, so for example, your material A is this one or material B is this one. So your main condition, because initially you should have some condition. Condition means you should have some goal. So our goal is to form a head of diameter D. If you want to make a form of diameter D, from a rod of diameter D, small d, the material to withstand a circumferential surface strain of ln d by d. Okay, so that means our condition should be it should reach, or it should withstand. It should withstand the surface strain of ln d by d. Right. So that means this is the limit. The dotted line is the limit. Okay, you have to cross that one. So now to you have to make some assumption. For example, let's say you have somebody is getting, let's say, 40 marks in the exam. So if somebody is getting 40 mark, but when you are calculating the grading, maybe A plus or maybe S or maybe A, you are calculating. So what you are doing, you are telling that when you are writing the 7 questions in the exam, or maybe 6 questions, so some students, they are confusing in the last 2 questions. Maybe first 5 questions are excellent. So 6 and 7, what they are thinking? They are thinking, if I will write 5, I'm not clear. Also, I'm not clear about the question number 6. 2 questions I'm not clear. But if I will write only 5, maybe faculty will give me maybe 4 or 5 marks. But at the same time, maybe some people, they are thinking, maybe if I write another question, maybe if that is good, because still I'm not clear. But if the teacher, they will find this is maybe much more clear, maybe he will give me 8 marks. So I have 3 marks extra. Right? So they are thinking alternative way. So here also what we are thinking, the strand path A, okay, in the bottom, the dotted line, in the bottom 2, I have mentioned strand path. The strand path A does not meet this criteria. So if you are thinking that the strand path A does not meet the criteria, so what you have to do? You will not stop the experiment. Okay, so you have to change to path B, another path you have to make it. But how you will change to another path? Because you have to add something. So what you are adding here? You are adding maybe lubrication here. So the moment you are adding lubrication, if you are changing the path, so maybe it is possible, right? Is it clear, the first one?
Yes,
right?
sir.
Okay.
Yes, sir.
The second, again, I'm not telling only 2 options are there. Maybe you can find another 3, 4, 5 option also. Okay. So the second option is a successful bolt head could be made with strand path A, because initially the strand path A was wrong. So that's why we moved to strand path B, right? But my point is now, if with the help of the strand path A, is it possible to make it? Yes, it is possible. But how? If the material change from A to B, for example, initial material was A, if I will replace the material A to another material B, maybe with the strand path A, maybe it is possible. Right?
Yes, sir.
Okay, so these are many alternatives just you can tell. I'm not telling only two ways are there, because the alternative way what we have we are thinking, or but within the limit of our parameters, within the limit of our material property or the material structure. Okay, you cannot go beyond that, right? Okay, yeah.
Okay.
So next point we have maybe when we are talking about the cracks also, I just mentioned, few cracks are there. Of course, we have already discussed about how to remove the cracks, how we are getting, of course, when we are doing any kind of material, you will find some crack. So a lot of testings are there. We have destructive testing, we have non-destructive testing. So this depends upon your material, this depends upon your cost, and depends upon your criteria or availability or feasibility, you can go ahead. Okay. So I just mentioned here, there are several cracks actually. So the cracks that occur in metal working process can be grouped into three broad categories. Okay, so one this kind of crack you are getting, and these cracks are the free surface. Okay, on the top surface or the free surface, you are getting some cracks, and the second cracks you are getting the cracks that develop in a surface where interface friction is high, such as in extrusion process. Okay, when you have, if you remember that the deformation zone picture schematic diagram I have shown, that this is in between the deformation zone. On the top side you have the lubrication, then both way you are finding some heat, and then also friction you are getting here. Okay, and then force you are applying from both the side. Okay, so also you are getting some cracks inside or the surface on the surface, not inside, on the surface, but where you are giving some friction, and that friction is much more high. The moment you are getting some friction high, you are finding some cracks there. Okay, and the first one probably you can get from here, like the free surface. Okay, but this is inside when due to the friction is high, right? And the third one, you have the internal crack in between, and the internal cracks such as the chevron cracks in drawn bars. The moment you are drawing the bars, so also you are getting inside. So that means you are creating some residual stress inside there, and that residual stress is high. So then you are creating some crack, right? So these are basically you are finding some cracks. But apart from this, also you can find, like whenever you are doing some experiment, so you will much more aware that, because we are just studying the literature. But based on this, you cannot distinguish only three types of cracks are available. Maybe depending upon the material and depending upon your techniques applied or your work style, then you are finding different kind of cracks, right? Yeah. So this is the last, also the residual stress also. I told you in the beginning also the residual stress, then how to make it a heat treatment. Then in heat treatment also, how which parameters are very important. Maybe like, the maybe in the next slide I will show. But just you can see that the residual stress, how you are getting. For example, if you are telling a rolling, let's say, so you are getting on this kind of surface, you are getting some residual stress here. Okay, so whenever your rolls are moving and your metal is passing from this side to this side to this side, so that means near to the passage, near to the surface of the passage, you are getting some residual stress, right? And the another way also you are getting, if you have the compression here, because two things are going, one is compression, you are pressing, and one is tension, because the opposite side you are finding tension. So now everything you have to, because if you read your thermodynamics part, so everywhere you have to think about the static equilibrium. Okay, so I mentioned somewhere the residual stress, whatever the system you are generating here with the help of the compression, this side, this small portion, this portion and this portion, and in tension you are getting this portion, and this residual stress generating with the help or with respect to the compression is equal to the, or is equilibrium with the residual stress obtained with respect to the tension. Okay, I mentioned here the residual stress system existing in a body must be in static equilibrium. Otherwise, it can be not balanced. It will be imbalanced. Okay, so these are some kind of residual stresses we are generating, right? So in the last slide, I just put already I have explained you maybe in several aspects. So whenever you are thinking about how to relieve the stress, of course you have to go for any hot forging we have discussed. Then also the annealing or maybe the heat treatment process, but commonly we are using. But at the same time also we have to think about all the the rates. For example, the heating rate you are increasing up to a certain limit, and that heating rate also should be controlled by you. This is depending upon the properties of the material. Let's say 2 degrees C per minute or 5 degrees C per minute or 10 degrees C per minute. Okay, so normally slow heating rate is required or is recommended. The second thing, whenever you are holding for some certain time, let's say 1 hour or 30 minutes or maybe 2 hour, 5 hour, that also you have to hold in that particular temperature. Let's say if you are maintaining 300 degree, so you have to maintain, because sometimes in furnace this is fluctuating. So the moment it is fluctuating, so that is also one effect. Maybe you can get some cracks there, or maybe you cannot find the growth properly there. And one more thing is, maybe, when you will do actually some research, you will get to know, because whenever you are using in a furnace some any kind of heat treatment, the furnace, there is a thermocouple inside, and that thermocouple is showing the furnace temperature. Okay, but whenever you are putting the sample somewhere in between the furnace chamber, and that temperature is different at that time, because the furnace thermocouple is somewhere in a far from that sample area. Okay, maybe far, maybe I think maybe 30 millimeter, or maybe 40 millimeter, or maybe 60 millimeter. But if you will put another thermocouple touch to the sample, or maybe 1 mm gap to the sample, then that temperature will be the accurate temperature, or the actual operating temperature. Okay, so you have to add one more thermocouple. That is also, many people, they are not considering that one, because they are thinking the furnace temperature is that one, so my sample is also heating at that temperature. No, this is wrong actually, right? And the third part, we have the cooling. Okay, whenever after holding, then you have to cool it. And the moment you are cooling, that cooling also, there should be certain degree or rate. Okay, maybe 5 degrees C per minute you are cooling, or maybe 10 degrees C per minute you are cooling, or maybe 1 degree C per you are cooling. Okay, and also sometimes we are cooling and we are quenching immediately. For example, after finishing, immediately we are putting in oil bath, or maybe water, or maybe like furnace cooling. Okay, many are there. So these are also, it will affect to your stress relief. Okay. So I mentioned here the differential strain that produce the residual stress also can be reduced substantially at room temperature by plastic deformation. Okay. So one more is, maybe if you will ask me, maybe I think you have never asked that one. So I mentioned just one line. We have not went in detail. The residual stresses are difficult to calculate with the precise by analytical methods, and therefore they are usually determined by a variety of experimental techniques. Okay, because sometimes when we are doing research, we need very accurate data. For example, if this is 23.243, means we need that value only, because that is the most accurate value. Okay, but sometimes, like we are just making round of 23.43, means okay, make it 23 or 23 or 24. Okay, so you have to take it the exactly value. Okay, so here it is very difficult actually to find out, but there is a method we known as the X-ray analysis. With the help of X-ray analysis, maybe you can, if you want to go for material characterization, maybe we have, the detail of the technology, or maybe the process, how, or the operating process, how we are making this one. So also you can go to this X-ray analysis. You can just study how actually they are making to, or they are finding the residual stresses. Okay, fine. Yeah.
Yes, sir.
Okay, so this is all about the metal deformation, the basic part. So I have one or two numerical, just you can do this one. The first question is the strength coefficient. Okay, can you see the question in the last? Yeah.
Yes, sir.
The
Yes, sir.
the strength coefficient is 75,000 pound for inch square, and strain hardening exponent is 0.25 for low carbon steel used in a forming operation in which the work part is reduced in cross-sectional area by stretching. If the average flow stress on a part equal to 30,000 pound per inch square, determine the amount of reduction in cross-sectional area experienced by the part. Okay, so just you can write what is the given value, then what should be the formula you will use, and then go for the calculation. Then if you cannot, then I will show the answer. So what is the value given? The strength coefficient is given, right? What is the strength coefficient?
75,000.
75,000, right? And then what is the strain hardening exponent is given? So that means n is given. Okay, 0.25. And then if the average flow stress is given, that means YF bar is given 30,000. Okay, so can you find the strength from there? What is the equation?
K epsilon power n by 1 plus n equal to average flow stress.
Yeah. Amal, are you getting?
Yes, sir.
Okay. Please do. At least strain you can find out, and then we will go the next step. Other people also please participate. Please do. Ayush, are you getting? Anyone got the answer of strain epsilon?
So could you repeat the formula again? I made a mistake in copying the wrong formula.
YF bar equal to K epsilon to the power n divided by 1 plus n.
Okay, sir.
Okay. YF bar equal to K epsilon to the power n divided by 1 plus n. So YF bar is given 30,000, and then K is given 75,000, and then epsilon to the power 0.25 divided by 1 plus 0.25.
Okay, sir.
Okay, so how much is epsilon? Anyone?
So 0.3, 0.3164, sir. 0.3164, sir.
Epsilon?
Yes, sir.
But I got the answer 0.0625. Is it wrong? Maybe just you can cross check again.
Okay, sir, I'll check.
Sir, what's the answer?
0.0625.
Yes, sir. Got that answer.
Okay. Because ln epsilon is minus 2.77. Yeah, others are getting, other student epsilon equal to 0.0625. Adil, are you getting? Aditya? Akash?
Yes, sir. It's 0.0625, sir.
Yeah, then fine. Okay. Then next part, yeah, you can start. Next part, what is asking? Determine the amount of reduction in cross-sectional area. Amount of reduction in cross-sectional area. Okay, so that means something you can make any equation which is related to or which is linked to epsilon, and reduction means A0 and AF. Okay, if an equation is there, epsilon equal to something A0 and AF, then you can take that equation. Yeah. You can see here. Okay, so what I mentioned here, so the value is given, YF bar is given. Okay, you can see the answer here, the explanation. So this is 30,000 and the equation is YF bar equal to K epsilon to the power n divided by 1 plus n. Okay, so YF bar is given 30,000. Then K is given 75,000. Okay, epsilon to the power 0.25, the strain hardening exponent, divided by 1 plus n, so 1.25, right? So you will get epsilon equal to 0.0625. Okay, up to now, I think is it clear for all. Then second is it is asking determine the amount of reduction in cross-sectional area. Okay, so if you know the equation epsilon equal to ln A0 by AF, so that means initial reduction area divided by the final reduction area. Okay, and this equal to 0.0625. So now you have to find out the amount of reduction, how much percentage it is reduced. Okay, so you can get it A0 by AF equal to this much, then AF equal to 0.9394 A0, and this much amount is the reduction of 6.06%. Okay, you can calculate from 1, so you will get 6.06. Is it okay?
Yes, sir.
Yeah, Achutan, okay, na?
Yes, sir. Yes.
Okay. Other student, only 2 students, Amal and Achutan. No others is participating. Bishopriyan, Benold. Is it fine, right? Okay, can we move to the second?
Yes, sir. Yes, sir. Yes, sir.
Yes, sir.
Okay, so you can go to the next one. Yeah. Yeah. In a tensile test, 2 pairs of values of stress and strain were measured for the specimen metal after it had yielded. Okay, so the first one is true stress equal to 217 megapascal and true strain equal to 0.35, and the second true stress equal to 259 megapascal and true strain is 0.68. Based on these data points, determine the strength coefficient and strain hardening exponent. So that means what you will find out, the strength coefficient and the strain hardening exponent. Okay, so that means one you will get n and one you will get a k. So you will get 2 equations in the beginning. Okay. Hello. Which equation you will follow?
Sigma equal to K epsilon power n.
Sigma equal to K epsilon to the power n. Yeah. Then you will find two equations. Okay.
Yes, sir.
Yeah, then two equation you have to make it, for example, the equation 1 equal to equation 2, then you will get n. Okay, so you can do. Then you will find K.
Okay.
How much is the n? Everybody is getting the equation, right? So equation you can follow K equal to sigma divided by epsilon to the power n. Okay. Okay, you can see. So I have taken the equation K equal to sigma divided by epsilon to the power n. This equation you know, right? Is it clear? This equation, you know this equation.
Yes, sir.
Okay, so you can find from here. So ln k equal to, if you can to make it ln k equal to ln sigma minus n ln epsilon, right? Because you have division, right? This equation is now clear. So if this equation is clear, so you have given your true stress is given in the first equation 217 megapascal and true strain is 0.35, right? In the second equation 259 megapascal true stress and the true strain is 0.68. So instead of this ln k equal to ln sigma minus ln EE, can you put this one ln k equal to ln 217 minus n ln 0.35, first equation. Okay, this one. Similarly, in the second equation, ln k equal to ln 259 minus n ln 0.68. Is it okay?
Yes, sir.
Okay, and this value ln 217 and ln 259, you will find some value there. Okay, so in the first equation, they got 5.3799 plus 1.0498 n. Because this value you will get, just you can put in calculator ln 217. So you will find 5.3799. Okay, other term you have to make it remain same because n is there. So n ln 0.35 is 1.0498 because you have to take the number. So at least one, if unknown is there, then you can find out. If two unknown, then it is very difficult. Okay, in the second equation again, so you will find ln 259 is 5.5568 and n ln 0.68 is 0.3857. Maybe you can cross check, maybe my value may be wrong. Is it hard?
No, sir.
Okay.
Yes, sir.
Who is it? Yes, sir. Is it hard? Yes, sir.
Sir, no, sir.
Okay. This is the easiest one. Simple, arithmetic what you have done in, I think in your 5th or 6th standard probably. Okay, so then if you have two equation, the first equation, second equation, so it is mentioned that in a tensile test, two pairs of values of stress are obtained, two pairs, right? So that means this value equal to this value. So now only you have 1.0498 n and here 0.3857 n. So can you find out n? N I got 0.2664.
Same, sir.
Yeah, the answer is correct, or maybe you are getting different. Vishnu, are you getting? You are silent this time. What happened? Anirudh? Ayush? Yeah, okay. So have you got n equal to 0.2664?
Yes, sir.
Okay, so if you have found n equal to this value, then you can put just in any equation. For example, this ln k equal to 5.3799 plus 1.0498 n, or maybe also you can put ln k equal to 5.5568 plus 0.3857 n. So if you put any one equation, don't go for the two equation, unnecessary waste of time. Any one equation you can just put. So you will find k equal to 287 megapascal. Do not forget the unit. You have to write the unit. Any equation you can put. Okay. Fine.
Yes, sir.
Yeah, okay. And everybody done? Achutan, have you finished? Satya? Vishnu?
Yes, sir.
Yeah. Okay, other student, please do it. If you have any difficulty, you can ask me anytime, not an issue. Okay. And the same PPT, whatever the PPT today I have shared, this is already uploaded in MS Team. Okay, you can download when you have free time, you can study. And the module is already working or not working?
Sir,